Good morning. So, today should be a relatively simple conceptual lesson. You already know what we're doing today. We're just applying the fundamental theorem of calculus, but to more difficult problems. For example, let me give you the first problem. Let's just jump right into it. Let's take the integral from 0 to pi over 2 of x sine x squared. And what you should realize is the only way to take the integral of this is using good old u substitution. So let's have some fun with this. Let's let u be the inside function, and the derivative is 2x dx. Therefore, if we sub it back in, the x's go away, and we're left with 1/2 sine u du. Don't worry about the limits. I'll talk about them in a second. If we take the integral, we then get negative 1/2 cosine u, which is negative 1/2 cosine of x squared from 0 to pi over 2. Then you can just plug in your values and get 0.89. In other words, there's really no difference compared to what we did previously. We just use substitution to get the rule, and then we plug in the values afterwards. That's one way. There is another way. I generally don't use this way, but in chapter 9 I'll use it a little bit because the integrals get more complicated and you'll change variables 2 or 3 times, and therefore it sometimes is advantageous for you to do it this way. The other way is to do it this way. Do exactly the same beginning here. We get the integral of 1/2 sine u du. And then what we can do is we can change the limits. For example, if u is equal to x squared and 0 was x, that means u must be equal to, if you plug 0 in, u would have to be 0. It's a coincidence that they're the same number. On the same token, if we put pi over 2 in here, we get pi squared over 4. You could then just solve it like we just did, but instead of putting x back in, you could put those numbers in instead. It's exactly the same thing. It's just a matter of whether or not you prefer to change the limits and not go back to x's, or do you prefer to go back to x's. There are some problems on the AP test where they force you to do it this way, but I'm not too concerned about those. We can see some of those problems later on. In the end, as long as you understand this, but if you or do either one, doesn't matter to me. So let's do another problem. Let's take the integral from 0 to 1 of x squared times 1 plus 2x cubed to the 5th. So again, let u be the inside function just like we always do. Du equals 6x squared dx. Therefore we get the integral of 1/6 u to the 5th du. If you want, you could then do 136 u to the 6th. So you get 136 times 1 plus 2x cubed, and evaluate that from 0 to 1. That would be one way. And the answer, if you did it that way, would be 20.22. Again, the other method, you could have plugged in 0. When you plug in 0, you would get, when you plug in 0, you get 1. And when you plug in 1, you get 3. The other way would be to use these two numbers on this equation. Again, it's up to you. Let's do another one. Let's take the integral from 1 to 4 of 1 over x squared, square root of 1 plus 1 over x. Again, inside function. And this one looks weird. You wouldn't expect that this is going to cancel out that, but watch what happens. If u is 1 plus 1 over x, the derivative is negative 1 over x squared. That cancels that out perfectly. Therefore, it's the integral of negative u to the 1/2 du. Let's just change the limits on this one just to practice it. If you plug in 1, you get 2. If you plug in 4, you get 5/4. So then we have negative 2/3 u to 3/2 from 2 to 5/4. Notice This number is bigger than this number. That happens when we switch the limits. It's just gonna, if we switch them, you have to make that positive. Don't be freaked out by that. And the answer then becomes 0.9556. Let's do a couple more. The integral from 0 to pi over 3 of sine of theta over cosine squared. You have to realize what the inside function is. The inside function is down here. So we have u is equal to cosine theta. The derivative is negative sine d theta, which cancels out that sign on top. So we're left with the integral of negative u to negative second du. When we integrate this, we get u to negative 1, changes it back to positive, from 0 to pi over 3. Oh, sorry, I didn't change the x's yet, I'm sorry. Cosine theta to negative 1. That's not the inverse. That is the actual secant. It's 1 over cosine. From 0 to pi over 3. That gives us 1. You would find that if you actually change the limits, often the trigonometric ones worked out prettier. These limits would have been 1 and 1/2, and 1 and 1/2 plugged into this would have been extremely easy. Give you another one. The integral from 0 to 13 of 1 over the cube root of 1 plus 2x squared. The inside function is 1 plus 2x, leaving us with du equal to 2 dx, and therefore we get the integral of 1/2 u to negative 2/3. I combine those exponents to get 2/3, but negative since it's on the bottom. So we get 3/2 u to 1/3 from 1 to 20, from 0 to 13. I didn't change it over to x's, I'm sorry. 3/2 times 1 plus 2x to the 1/3 from 0 to 13, which gives us 3. The next problem. Let's do a couple quick ones here. This is number 6. Integral from 1 to 4 of x minus 1 over square root of x. The goal of this problem is to remind you that u substitution really is a backup method. This problem is nothing more than dividing this up. Therefore, if we divide up x negative, or maybe write it like this, some people prefer doing it like this, we multiply this in, we get x to the 1/2 minus x to negative 1/2 dx from 1 to 4. If we now integrate this, we get x to the 3/2, 2/3 in front, minus 2x to the 1/2, and evaluate from 1 to 4, which is 2.66. And the last two problems I want to bring up is just to make sure we're good with something. 7, 8. I want you to see them side by side. The integral from 0 to pi of sine of x squared dx, and x, the integral of x sine of x squared dx. The difference is at x, and the whole reason why I bring these two problems up is I want you to realize which one is u substitution. The one over here, we need u substitution because it cancels out the x in front. The one over here is physically impossible. You cannot do it. You need to use your calculator, and we'll go back to that in a second. Therefore, this is u, this is the derivative. It becomes the integral of 1/2 sine u du, which is nothing more than negative 1/2 cosine of x squared from 0 to pi, which is positive 0.95. On the other one, we need to pull out the calculator. And sometimes in the AP test, they do give you impossible ones to do by hand. So you have to actually use the calculator. You hit math. Let me get my keyboard up here. Hit math. Just where the derivative is, same idea. And derive, this stands for numerical integral. I'm not sure what the F stands for. And this may be the notation you have. Most of you guys using newer calculators, this will be it. 0 to pi sine x squared. I must say I like the integral notation here just because it really just shows you exactly what you're writing. So it should line up perfectly. Press enter, and you have 0.18. Which doesn't agree with my answer on my sheet. My guess is this calculator is not in radians. No, it's not. .773. If you're using the other notation, if your calculator is an older calculator, it would look like this: fn int parentheses. You would type in sine x squared, so this would be the function, with respect to x, which is what the dx, basically this is the dx part, comma, 0 to pi, the limits. So in other words, you're setting up the integrals. The integral from 0 to pi of sine of x squared dx. That refers to that, this refers to the function, and these two refer to the limits. So for homework tonight, worksheet 4.6, numbers 7, 21, 23A, 24A, 31, 33, 40, and 42. Again, I'll post the answers on the Chapter 5 note on the e-board, and you guys should be set. I think in the end, even though I've been absent the last 2 days, these two lessons probably were ideal, especially today. There's really nothing new here except plugging in the limits versus not plugging in the limits from about a week ago. So I'm not concerned about this lesson at all. The other lesson obviously was a little bit different, but I think you guys can handle that. I think my notes were pretty in detail. So anyhow, do the homework, come in with questions, check your answers, come in with questions of course, and on Monday we'll do a real quick touch up if we have to on any of these concepts. I thank you for bearing with me on these last 2 days, and enjoy your weekend.